Hi, my name is Ryan Thompson, and this is my midterm assignment for CPSC 5210. I've got 6 questions, a few with some sub-questions. Question 1 asks you to use the master theorem to find use the master theorem to find its asymptotic bounds. So, given the master theorem form, A is equal to 16, B is equal to 4, f of n is equal to n squared. F of n, here we're going to try and see if f of n is equal to n log b a. And here b is 4, a is 16, and these two, the forms work out n squared equal n squared, which is true. So this falls into case 2. Therefore, the total runtime is equal to n squared log n. The second part of this question asks you to use the substitution method to validate this asymptotic assumption, asymptotic bound. So what we'll end up doing, usually you have to guess, but now you don't have to because you've already solved it with the master theorem. You'll take here this term for the number of subdivisions and plug it into the theta. So for the upper bound, once you've plugged it in, you're trying to see if it's less than, if the total runtime is less than or equal to that formulation. And so once you've plugged it in, you'll carry out the math, which is square terms, distribute the 16 across, take care of the log, and you'll have the n squared. And then once you've done that, you'll get down to this form. But you can take the n squared, and what you end up doing is creating this term here. And that kind of helps clarify if you can make this piece less than this piece, and you can for c greater than or equal to 1/2. So 1/2 is kind of the break point here. If it's 1/2, this term becomes 0, and these two become equivalent, so that holds. If this is greater than 1/2, this stays negative because it carries so much more weight than just n squared. And you'll have this this be true, that it's less than c of n squared, because this will be a negative term. Now for the lower bound, you're trying to prove if this term, the substitution, is greater than the total runtime. But the math is essentially the same. You get back down here after carrying out the terms, or carrying out the math, and now it's kind of the opposite, but only for c. Because you're trying to prove that it's greater than, you want c to be less than 1/2. So instead of trying to keep this negative, you're trying to keep it positive so that this term is always bigger than or equal to this term. And so both of the upper bound and the lower bound come out to be c n squared log n. So big O is equal to theta, or omega, which is equal to theta n squared log n. Question 2 is use the master theorem to find the asymptotic bounds. So we're given this total runtime. Familiar with the master theorem by now. So A is 1, B is 19 over 3, f of n is equal to n, because f of n has to be a non-negative function. And 5 seems like a trivial, almost like a trivial, because it's a constant. So a lot of times our constants are just handled out separately, or they're kind of brushed aside for the simplifying assumption. So plugging this into our standard approach for the master theorem, the n raised log b of a, when that reduces to n0, which is 1. So now we're going to check this ratio to see if it's polynomially bounded. You can see it easily, but we check here. So n divided by n log b of a, you get n over n raised to 0, which is just n. So of course, that's really n raised to the 1, so that means there is an epsilon that exists such that f of n is equal to n log b of a plus epsilon. So that's case 3. Now case 3 has another assumption that you can check as well. So here is the form that we're going to check, keeping in mind that c needs to be less than 1. So once we substitute in our a, b, and f of n terms, we can see that as long as c is greater than or equal to 319, this holds. But again, it's got to be less than 1. So here we've bounded C. And for substitution, we can plug this in, and you can see that once we have n and we separate the n term, we consolidate the n here, you're left with a constant term, and so you can let c prime be this constant, and now you have n times c prime. Question 3. Assuming you have a task to sort the telephone numbers of a major carrier. So to sort the telephone numbers of a major carrier, I would use the bucket sort. The first reason is that it is not a comparison sort. And by theorem 8.1, all comparison sorts have a omega n log n for the worst case. So a linear sort is the better choice. So this is kind of their lower bound. So what we're trying to do, and we know that other sorts can beat this lower bound, so we're going to go towards there. But it's helpful to point out that anything of the comparison sorts has this kind of asymptotic lower bound. Between the 3 linear sorts that we've studied, we have counting, radix, and buckets. And theta, the theta is not equal for all of them, as you would guess, because they're different procedures. Since counting sort is theta n plus k, where k is the largest value, and telephone numbers in the United States are at 10 digits, that would make the array extremely large, and you would end up with a lot of wasted space when you're trying to do the frequency counts for each integer 0 to k. Radix suffers from a similar problem of the memory requirements because all of these are stable, so you have to keep lists going that keep them in the original, that have information about their original order. So radix is theta d n plus k, or d is the number of digits, and k is the number of values a digit can have. Then radix becomes theta t, or 10 times n plus t, which is theta tn plus 100. So that's also a very large, it's larger than the other linear sorts, but it's also a large memory requirement. So that leaves bucket sort with an average case of theta n, and that's the best option to give the runtime and the memory constraints. Now, even though this average runtime is very good, I just want to point out that the bucket sort does have 2 assumptions. One is the range, and one is the distribution of which your sample comes from. So to address the first part, the range, of course, of telephone numbers is not between the standard 0 and 1, but that's really a trivial transform. With just a little bit of information of the max and mins, you can transform this easily into that range. Now, the CLRS textbook points out on page 202 and 203 that the linear expectation for the size of each bucket holds regardless of the number being from uniform distribution. And I bring up this point because telephone numbers have area codes. Area codes correspond to populations, and as everyone knows, that the population is not uniformly spread through square area, so that there's pockets of high growth major cities. So a given area code may have more than another area code, which would indicate a non-uniform distribution. So that's why I bring up that assumption, to show that even if those two, even if the second one is relaxed, it still is a valid to this problem. Question 4. We're asked to modify merge sort, the standard definition in the book, to merge triple sort. So there's really only a few modifications that need to be done to get this running. So instead of dividing the range P of Q, or P and R, by 2, I divide by 3. You have to call the merge sort one more time here, and you also need to create the 2 bounds. So you've got P, and this is the first third. Then you have the second third start to the end of it, the end of the second third to the last value, and then you merge them all back together. So we actually have having to modify this. We're also given the assumption that sorry, you're not giving that assumption. I'm stating that Q is a valid size given that the assumption n equals 3k and a is always divisible into 3 equal size. So that's an assumption that we're given at the start of this problem. So because these are powers of 3, everything is going to work out nicely in terms of dividing them down. And because they're always divisible by 3, until you obviously get to one element, they're always going to have the same size for each one, so you really only need to calculate the size once. So instead of, for merge sort that only has 2 subdivisions, you need a left, middle, and right here, and they're going to be all the same size. So now you can use one loop to iterate through, as long as you just clarify which element of A they're supposed to start at. So that's pretty straightforward because you're just adding a fixed width to a different starting point. So here you have P plus I minus 1, P plus Q for M, and P plus 1 plus 2Q for R. Now, you would have an empty spot at the end, but we fill that empty spot with this positive infinity so that when you're doing these criteria, these logical evaluations later, you have some ultra max number that you can't go beyond. So even if you reach the end of L first, it'll always be evaluated and won't throw off the code. We'll use 3 iterators, I, J, K. So before there were only 2 iterators. We'll still loop through the initial part passed in by the user, P to R, the initial elements of A. And we'll look here. So I've got 3 different criteria that we go through. Each one just trying to capture which of the 3 subarrays, left, middle, right, is the minimum. So here in this hierarchy, it's R, M, L, L being the lowest. So A of M is L, and that uses I, so that iterates forward. Here in this one, the hierarchy is R, L, M, M being the lowest, using J iterator. So A of M is equal to M of J, iterate J forward one. And here, it's L, M, R, R being the lowest, K is equal to K plus 1. So it follows the same exact procedure. The only extra bits here are trying to figure out the right starting bounds and consolidating the loops, and then doing the extra logical evaluations. The second part to this is please find the asymptotic bounds for runtime of the merge triple sort. So following the textbook's outline, the general formulation is A, T of N divided by B. So that's the number of subdivisions and the number of times it's subdivided, plus D, which is actually calculating how wide the subdivision should be, plus C of N, which is your time required to combine them. The D of N is for the computing the subdivision of each array. This is a constant time, so it's state of 1, which we'll end up brushing aside because when things are that small in comparison to the size of some sufficiently large n, it really doesn't make any difference. So that assumption is ignored, or that contribution to this whole time is ignored. And since the recursion solves 3 subproblems, each of size n divided by 3, it contributes 3t n divided by 3 to the runtime. The combined time is Cn equal theta n for n element subarray. So here this follows the standard procedure, just like when it was divided by 2, now when it's divided by 3. So the recursion tree would follow the same path. The formulated merge triple sort has 3t n divided by 3 plus theta n. Since t is a constant, it can be ignored, and it's so trivial to the overall total runtime. Using master theorem, a is equal to b was equal to 3, which is the standard for merge sort. A and b are always going to be equal for a merge sort. Now f of n is equal to n, so n log b of a equal n to the first, which is equal to f of n, which falls into case 2. So now your theta, your runtime, is equal to n log n. Question 5 is please modify the count sort to account for this range -n to n. And that's actually a lot of information right there. So you really don't need to modify the initial algorithm too much from the book. So since the max of A, which is n, is also equal to the absolute value of the minimum of A, there's only a few adjustments needed. So initially you'll have your count, your C, be from 0 to K. But since this is, let's just, for the sake of argument, say that it's symmetrical from -n to n, then you can see how it becomes 2K for the total width, since K is the max. So for I is equal 0 to 2K, you'll fill up C with 0 because later you'll be adding to it. You can't add to an empty number or a null number. So from I to 1 to A dot length, all you really need to do is just, you'll index into A. So indexing into the element doesn't change anything. But now when you get the value of A, you'll add K so that you can find the appropriate element of C. So even if the first one, is -n, because -n plus K, which is equal to n, becomes 0. So you get back to C of 0 in the most extreme case. So in the most extreme case, you're at n. At the uppercase, you're at 2n or 2K. And you can see here that indexing works well as long as you don't get it inside. So A of J plus K, you're still going to stay on track. So now for I equal 1 to 2K, you're going to go through and you're going to create the cumulative sort. This should be just end. The SS was just a typo. The C of I equals C of I plus the one prior. So now you're creating this cumulative sort. And now you're going to use this same indexing as you did in the original source code or pseudocode. Now you're just going to add K to it. That gets you into the correct C, which puts you in the correct value of B. And then you'll decrement here, you'll decrement C by 1, again using this indexing procedure as done throughout this code. So really there's not a lot of adjustments need to be made because you're given a lot of information about the range of A that could come on. There's really only a few little tweaks that you would need to do to make this a little more robust to beat any -n to n value. And that would involve, if you're wondering, that would involve having another one here that would pass in the minimum value of A, and then you would just need another step to create that. So question 6 is please modify the bucket sort pseudocode on page 201 in the textbook so that it can do floating point numbers. So this is also, again, a lot of information that you're given to start it out. Well, since the max of A is less than the absolute minimum of A, only a few adjustments are needed. This is standard from the last algorithm, so you have the total length. M is equal to the absolute value of M, so your -50 is your min. Now the absolute value is 50. Now we know it doesn't exceed 50, so now you've created the upper bound as well. So we'll let B be 0 to n minus 1, and as you loop through from 0 to n minus 1, you make B an empty list. Not an empty array, an empty list, so that you can hold multiple values in there in a ragged sense, because they all won't have the same size. So for I equal 1 to n, we're going to use this new variable key, which is AI plus m. So you're shifting, you're adding 50 to, for example, the lower bound. So now you're at 0, and for any value, you're dividing by 2m to put it inside the bounds of 0, comma, so bracket 0, comma 1, open parentheses. So this is in the case where you have the number that's just under 50 and you divide by 2m, that would be 100 in this case. You have nothing that would equal 100 even when you add 50 to it. So you'll never get to 1 because that's your maximum value here, this condition holds. And so because you never get to 1, bucket sort will work with this adjustment. So once you've got this scaled, that's really all you're doing. You're scaling it. You'll multiply it again to follow the standard bucket sort procedure. And then this can carry on through. You'll concatenate as you did last time. There's really no issues here. Now, you got to remember that once you get to B and you've got this concatenated, sorted, very nice B, you need to transform B back to the original values, because if you return B to the user, it doesn't work anymore. So after you've got B concatenated together in the proper order, you'll just need to do the reverse order of operations back into the original values of A. So you'll and because this is just these are just linear transforms, you don't have any problems with not having a one-to-one correspondence. So this procedure works able to know the bounds ahead of time. If you did not know the bounds, this would be rather hard to know what the maximum could be. You would have to pick some number, do a test to find the maximum of this array. But the problem is that would take quite a bit of time as well. But here, the min works because you know what the lower bound is, because this bracket for the including, where the open parenthesis says not included. So you're not exactly sure what the maximum could be. You could have some very comparisons to do. So again, the trick is though, because what you fed into A or fed into B is this has been transformed, you need to untransform it, if you will. You need to reverse the order of operations that the key variable was scaled by to get back to the original values of A. So that's my 6 problems for my midterm assignment. Thank you.